Hi, I'm Benny D, and in this video we're going to have a look at limits and continuity. Okay, so a function is continuous at a point x equals a if f of x is defined at a and the limit as x approaches a of f of x equals f of a. So what that means, and we'll get to what limits actually look like a little bit, that as we approach some value a from either the left or the right, okay, we should be getting the same value as when we sub that value of a into our original function f of x. Okay, there's a few rules to these. Okay, I call them the limit rules. Okay, and they're really straightforward type of things like the limit of x approaching a of f of x plus or minus g of x is the limit as x approaches a of f of x plus or minus the limit as x approaches a of g of x. So, we can break these things up. Okay, if we've got the limit as x approaches a of k times f of x, well, that's equal to x times the limit, k times the limit of, as x approaches a of f of x. So if we can times it by a constant, and that constant can just come out the front. Similarly, if we've got two functions multiplied together within our limit, then we can do each one separately. And the same is true for when we divide our functions. So the limit as x approaches a of f of x on g of x, we can do each one separately and do the division. Okay, so I've got a couple of examples here to have a look at. So we've got the limit as x approaches 2 of 3x squared. Okay, so all we're going to do is actually sub 2 into 3x squared. Okay, so we'd say that equals 12. Okay. That's the most straightforward one. We get to ones like this, it's a little bit more complicated. Okay, so what we need to do is look at factorizing this. Okay, because if I put 2 straight into this function, it's actually going to equal 0 and it's all going to be undefined. So we just need to be careful with some of these. And we see if we do 2x take 1 times x take 2, we can factorize the top line, our numerator over x take 2. Okay, the x take 2's disappear. So the limit as x approaches 2 of 2x take 1 is equal to 3. Okay, and that's true for all x excluding 2. Okay, so just because this function, we've got to make sure that we're understanding that we can't do it at the point x equals 2. Our last one here is our limit as x approaches 2 of 4x times x plus 2. And the idea with this one is just to illustrate that we are allowed to separate into parts and do those parts separately. Okay, so when we put 2 into here, we're going to get 8. When we put 2 into here, we're going to get 4. So multiplied together, we get 32. Okay. What really aids with this work is looking at what it looks like visually. Okay. So this is all about when we have functions that are continuous. Okay. So we do this limit stuff so we can get to this idea of continuity. Okay. So all polynomials are continuous. So if I've got a cubic here, okay, we can see that there are no breaks or gaps. Okay. And if I was to put some value a into our function here, I get this value f of a. Okay, and if I approach this, so taking the limit from the left, okay, so as our function approaches a, it is going to equal f of a, and that doesn't matter if I come from the left or come from the right. Okay, so that's nice and continuous. Okay. If we have it look at something like a hyperbola. Okay. I'll have it one that's translated across a little bit so it's a bit easier to see. Okay, well, got a problem here. Okay, so for this one, at this point A, okay, for our asymptote, the function is not defined. Okay, so it's not going to be continuous for a start. Okay, but we can see that our limits approach different values. So this way it's going to approach negative infinity, and this way it's going to approach positive infinity. So we're going to have a problem there anyway. Okay, we can also have things like this going on. I'll do some axes. Okay. Okay, so this function would be discontinuous because we're not included at this point here. Okay, we've got a limit that is approaching both ways, but this point is excluded. Okay, so even though that my limit is going to be telling me I'm getting this same value from the left and the right, it's not defined at that value. Okay, so that one would be discontinuous. Okay, and we could have things going on like this. Again, we're actually defined everywhere now. Okay, sorry, this one of these should be open dots. Okay, and this is at A. Now, we are actually defined at all values for x here. But you can see as I approach from the left and as I approach from the right, I'm going to get different values. Okay, so even though the function is defined at our point A, our limits are different each way. Now that is a really complicated way of saying something that makes it really easy to remember if a function is continuous or not. Okay, if you can draw your function without taking your pen off the page, it's going to be continuous. Okay, that's your easy way of remembering it. Okay, but we need to be more formal in our mathematics here, and that's why we've got these rules and this process with our limits. Okay, you'll see that this is going to become applicable in our next video about applying this to differentiation. So hopefully there'll be enough to get you through some questions on this section.